Chapter 6, Section 2, Data Visualization for Univariate Analysis, Part 2. As the second section, let me show some visualization methods for univariate analysis of continuous variables. This section focuses on one of them, histogram. A histogram is a figure used to visualize the distribution of a continuous variable. In other words, a histogram is a graphical representation of a frequency table for a continuous variable. A histogram graphically shows how each observation is distributed along by the range of values of a specific variable. Similar to a frequency table, a histogram organizes each observation into some classes, and it indicates how many observations belong to each class. This is a histogram created by using the same dataset from the frequency table. It is a dataset of 50 students' exam score. In a histogram, the horizontal axis represents the classes. A class is the interval, not an actual value. And the vertical axis represents frequency. Here, we set the class widths to the same as those of the previous frequency table. For example, this bar represents the frequency of students whose score is greater than or equal to 40, but less than 60. By looking at this histogram, we can easily see that many of the students scored between 40 and 60. A bar in a histogram is usually called a bin. Each bin represents how many observations belong to each class, that is, the number of observations fall within the class. A histogram can show the distributions of the data clearly. As we know, not all datasets have a symmetrical distribution. By displaying data distribution using a histogram, we can see whether the data distribution is symmetrical, left-skewed, or right-skewed. When you create a histogram, you may wonder how to determine the class width, that is, the number of classes. Let's consider this issue using the previous data of 50 students. If we create a histogram of this data by setting the class width to 5, the histogram classifies the data into 20 classes. Here, some classes have no observations, and the histogram as a whole is a bit hard to see, maybe because the data is divided into two small classes. So, what about if we set the class width to 25 and classify data into 4 classes? As we can see, it is a too rough picture. The width is too broad, and thus it loses much information from the data. So, it is hard for us to get the whole picture of distribution by this histogram. So, how should we determine the class width? The answer is, there's no one best way to determine it. It is often determined based on subjective visibility. And it depends on the sample size and is sometimes determined based on practical conveniences, such as good cutoff point and understandability. If you have trouble in determining the class width, you can use Sturge's formula. This formula is designed to determine the number of bins, so by using this formula, we can determine the class width also. According to this formula, the number of bins equals 1 plus log base 2 of n. Here, n represents the number of observations. In this dataset, the number of observations is 50. So, we can find the appropriate number of bins by adding 1 with log base 2 of 50. So, it is 1 plus 5.6, so 6.6. So, the appropriate number of bins is 6 or 7. In the previous histogram, we set the class width to 20 and so the number of bins is 5. It is fewer than the value suggested by Sturge's formula. But in this case, setting 5 bins is reasonable because the class width of 20 is a good cutoff and easy to see the distribution of students' score. In histograms we have seen so far, the vertical axis represents frequency. They are sometimes called frequency histograms. A weakness of a frequency histogram is that it is sometimes hard for us to compare the distributions of different datasets. Suppose we have datasets that are widely different in sample size. If we use frequency histograms, it is not easy to see the similarity or dissimilarity between them. In such cases, it is useful for us to create histograms that assign the relative frequency on y-axis instead of the frequency. Such a histogram is called a relative frequency histogram. By using a relative frequency histogram, we can compare multiple datasets using the same vertical scale ranging from 0 to 1. So, we can see the degree of similarity between datasets more easily. By creating a histogram, we sometimes encounter variables with only one peak in their distribution. It is called unimodal data. In other cases, a histogram shows 2 or more peaks like this example. We call such data as multimodal data. In particular, we call a dataset with 2 peaks as bimodal data. When we encounter bimodal data, the dataset may contain 2 groups with different properties. Suppose the histogram on the right is from a dataset of females' height and the distribution has 2 peaks. And suppose this data contains samples of elementary school students and high school students. So it contains 2 different types of distribution. A frequency histogram looks like a count plot. A fundamental difference is that while a count plot visualizes the distribution of a categorical or discrete variable, a histogram visualizes a continuous variable's distribution. Since a count plot visualizes a categorical or discrete variable, its horizontal axis represents categories or discrete values. So, each bar is created for each category or each discrete value. Therefore, the bars are located a little apart. On the other hand, since a histogram visualizes a continuous variable, its horizontal axis represents a continuous scale. So, each bin is created for each class, not for a specific value. So, the bins are in contact with each other. Besides, since each bar represents the frequency of a specific category or specific value, we can identify the mode from the count plot. For the same reason, we can also identify the category or the value with the fewest frequency. However, since the bins in a histogram represents the range of a class, not a specific value, we cannot identify the mode from a histogram. Thank you for watching. Please thumbs up and subscribe to my channel.